guys, a very happy morning to every one of you guys. Today we are going to start one of the wonderful subject that's named as fluid mechanics. And today, mostly in this entire playlist, I would like to each and every viewers to watch the entire playlist, because most of the sector, because most of the point of view, it as I also learned from one of the top legendary teacher whose name is SK Mandal, and he is one of the top elite group person. It means in a teaching point of view, whenever you have any kind of doubts or whenever you have any kind of things, you can almost approach to him in a easy way. So most of the times I used to learn a lot of things from him. So from his point of view and from my point of view, I am just going to explain this entire fluid mechanics to you in a easily affordable English way. So guys, this entire fluid mechanics is especially I am just requesting, it means to watch the entire viewers, because the entire fluid mechanics I am going to tell in my point of view, because there are a lot of affordable teachers and affordable other it means academy that been teaching this fluid mechanics. So if you have any interest, you can go and visit there, and it's my general request, you can also visit SK Mandal sir to learn some kind of few things from him. But this entire fluid mechanics playlist is especially done from my point of view, because for easy understanding and for easy conceptual learning, I made this entire playlist for myself. So okay, suppose if I upload this kind of video to you, you can understand a little bit of fluid mechanics in your point of view. Okay guys, without going much into detail, let us get started, and from the blessing of the SK Mandal sir. So this fluid mechanics chapter is generally holds nearly 6 to 8 marks in the gate point of view. Okay, what is fluid mechanics? Fluid mechanics is the mechanics of liquid and gas either at rest or motion. Very simple guys. Fluid is combination of both two types of things. There are three matters. One is solid, liquid and gas. In that, liquid and gas alone comes under the, it means this liquid and gas alone comes under the fluid category. So we deal upon with this liquid and gas in our entire fluid mechanics subject. Suppose if this is a pencil, if I am moving this from one point of view to other point of view, so I am just applying a work upon this solid body. Suppose if I am just pouring some kind of liquid here, for example, let us consider like this. You can see. Oh my god. Okay, this is one small liquid. So this is a liquid. So what I am just doing is I am just pushing. It means I am just moving this liquid. So you can see here the liquid moves from one point of view to other point of view. So this is as like fluid mechanics. It's just a simple, a short representation. So when you see in the dam point of view, the liquid is moving and the turbine is rotating and we are generating power. So that's called as fluid mechanics. So the fluid mechanics line which deals with the behavior of fluids in the motion or rest. So that's called fluid mechanics. So the fluid is a substance that can form or deform continuously under the action of shear force. Whenever we apply a shear force over the fluid body, it means as I demonstrated a little bit of experiment, while I push the water, it just moves from one location to other point of location. So that's called, it means when we are applying the shear force. So shear force is simple guys. You just make this down body in a fixed way and you apply in a topward and external force. So the body tends to move. So this is solid. So you just see comes into the liquid point of view. You just place a liquid over here and most of the down surface will be little bit attached to the ground body. So you are applying shear force upon here or blowing air. So now the fluid tends to deform. So this is called as, it means the fluid is a substance that can flow or deform continuously under the action of shear force. I think so you can understand. And so the fluids, it means the fluid, the rate of deformation is more important than deformation. Rate of deformation means with the time we just represent to each and everything. It means with the dt, we don't know about differentiation. With the rate of deformation we use to align. And it means the viscous behavior is a characteristic of fluid. When external force applied to them, they continuously deform. Suppose guys, if whenever we apply any kind of shear force to a solid, it doesn't, it means deform easily. But whenever you apply shear force or any kind of force to a fluid, it easily deforms. So you can see, yeah, solid has a definite shape, but fluid has no definite shape. Yeah, solid can resist an external applied load. It means whenever you apply external force, you can resist, but a fluid can't resist. It's so much difficult to resist. So that's why it's been distinguished here. See, when a constant shear force applied, a solid eventually stops. It means deforming at a fixed angle. Suppose if I'm just, this is a pencil, this is solid body. If I'm applying a shear force upon it, I'm just fixing it down. And just applying means you can see this is little bit inclining and comes to the original shape. It's just for representation, I'm just moving like this. But in actual case scenario, you can do and you can find it out. So, but in fluid, you can't, whenever you apply shear force, it just travels and it just moves from one point of view to other point of view. So that's why the fluid has only resistance to compressible load. Whenever you take a fluid and you just compress it, it can't compress. But whenever you just make the fluid it means to give an external force, it can continuously deform. But also you can also, it means you can, for fluid you can't put a tensile load. The tensile load means it's so simple. And means parallel, it means parallel force in a opposite direction. But when you comes under the it means for compressive force, we are just compressing it. You don't know about what is the meaning of compression. So here there is given the difference between liquid and gas. So liquid has a definite volume, because you would have known when you carry the water in the water bottle, it has a definite volume. But gas doesn't have any kind of definite volume, so it expands in each everything. And for gas there is no surface, it means no free surface. For liquid it has free surface. Free surface is so simple, guys. You just take a water bottle, pour a water in it. Suppose the water bottle is 1 meter and the water consumes 0.5 meters. Mean here you would have known about this is called as free surface. So when you just see in any kind of it means water bottle, you would have assumed like this, there is a free surface. And temperature and pressure changes has no effect on the volume of liquid, so that's a good thing. So but when you heat a gas, you just see, guys, when you heat a gas, it expands so much rapidly, and when you apply a pressure on it, it expands and it goes in a so much faster way. And liquids are very much difficult to compress, and but gases are very much easy to compress. So in this question you can see assumption and the reason. In fluid, a rate of deformation is far more than important than total deformation. Yes, the rate of deformation is more than important than we deform it. A fluid continues to deform so long and external force. Yes, both are correct. Both A and B are individually true, and R is the correct explanation of A, because B is upon this only this kind of thing is acting. Okay, I think so you can have a basic overview on it. So as we proceed, we will definitely have a basic understanding and what the fluid mechanics is, especially coming to trying to tell to us. You can have a basic overview upon it. Okay, next one is the concept of continuous. Guys, concept of continuous, so it really so simple. It's like a continuous description of matter where properties of matter are considered as continuous function of space variables. It's for I'll just it means study. It means I'll just read it out and later I'll explain. Although any matter is composed of several molecules, the concept of continuum assumes a continuous distribution of mass within the matter. Suppose, for example, you just take this is a pipe, and when the water flows, most of the water gets sticks over it, and here the water gets sticks, but at the center portion the water just moves out. So you just compare to the gas also, here the density difference will be different, here density difference, here density. So each and every layer the density will be different thing. For example, water do have 1000 kg meter cube of density, but when it is flowing, here as the density gets stuck, the pulling and pushing may occur. So here the 1000.1, here 999.8, here 999.7, so here 1000.01, like that it will be. So little density variation. So under the concept of continuum, we just assume each and every sector comes under 1000 kg per meter cube. So that's why we just consider the concept of continuum in a easy and essential way. So it means this is the differentiation of density of limit. It means volume tends to 0, m of del v. So if del v is very large, it means if this kind of thing is very large, the density difference will be so much lesser. So you would have known about a lot of bigger containers. When we carry a lot of gases in it, as the volume tends to be so much large, the density difference goes so much later. So this is the thing that we need to consider, the concept of continuum. And in the concept of continuum, one thing is so much characterized. So you can see it is the distance between the molecule which characterized by the mean free path. So whenever there is a two molecule, there is a similarity between the difference between both them. This is the characteristic length. So we need to look upon that also. There is another thing called Knudsen's number. One of the most important thing to consider, because if Knudsen's number, it means is more than 0.01, our concept of continuum doesn't valid in the fluid mechanics. So we need to first relate the Knudsen's number. In our case, it means as we study in the fluid mechanics, all the fluid mechanics subject we usually do study is Knudsen's number will be less than 0.01. So I think so you can understand. Suppose if more than 0.01 comes, mean the concept of continuum does not hold. So that's why we usually read this Knudsen number less than 0.01 in the entire fluid mechanics. So Knudsen's number formula will be del, it means lambda divided by length. So lambda is mean free path and L is a characteristic length. So it describes the degree of departure from the continuum. I think so you got a basic overview. Suppose if Knudsen's number is more than 0.01 means the entire fluid mechanics you won't read. The concept of continuum it's not valid. If the Knudsen's number is less than 0.01, our entire fluid mechanics we will just study and we go based upon that thing. I think so you can have a basic overview upon it. So next thing is one of the most interesting thing, no slip condition, and because you can see, guys, this is a plate, and you can see, wait, I'll just make it an easy elaborated way, so you can have a basic overview in it. Okay, this is the main thing, and I'll just write a fluid mechanics, and today's date is 8th August 2025. I'll just put a line over it so for a basic easy understanding. So this is the thing, and you can see this is a plate, and still now there is no fluid upon it. So now I'm just putting the fluid. So while the fluid is being done, so you can see At the top sector, the fluid will flow easily, but at the bottom sector, the fluid won't flow because there is the friction. It means the friction usually goes unattracted. Whenever you just see in the ponds or lakes, the down portion of the liquid won't flow easily. It means you just visualize the down portion of the liquid won't flow easily, but the upper portion of the liquid flows so much easily. So that's why it's being represented here. Here the flow will be so much uniform. So until to reach, it means for example it's 1 meter. After 1 meter, here from the top sector the velocity will be 10 meter, means here the continuously here 0 meter per second, here 1 meter per second, 2 meter per second, 3 meters. So after a certain point of view, the velocity will be so much constant. So that's why we need to look upon this no slip condition. So this has been represented because here it means you can see here the zero velocity at the surface. Each and everything the velocity will be zero at the surface. So this is also known as you can see a fluid in a motion comes to complete stop at the surface and assume zero relative velocity. It means from the entire point of view in the fluid mechanics, we assume no slip condition. It means the velocity will be each and everywhere the velocity will be uniform. Like that we used to consider and we used to go. So I think so you can have a basic overview. So as the subject is proceeding, I will just explain. And the other point of thing is density. You would have known about the density, and density equal to mass by volume. So for mass we put a kg, and for volume we put meter cube. Suppose guys for weight and all, the unit is Newton. The unit is Newton. So that's why one of the most interesting thing. So and for it means for density and specific weight are the most important thing that we need to look upon. Specific weight. Specific weight equal to weight of the fluid. It means weight of the fluid divided by volume. It means volume of the fluid. Weight means what is the formula of weight into mass into gravity into volume. So mass by volume equal to density into gravity. So specific weight equal to density into gravity. This is one of the important formula that we need to look upon. So for example, what is the dimensional formula? For first SI unit means we can easily just represent. See, this is mass and this is volume, and the entire mass into gravity is Newton per meter cube for this. And for MKS unit and for dimensional formula is that's so simple. For Newton, what is the unit? It's like for Newton means kg, and dot gravity, for what is the formula of gravity? Meter per second square. So divided by meter cube. So now we just make a cancellation, and what it comes kg and kg, and this is second square, and meter, and so here it will come meter per minus 2. So it means it will go upon, so m1 L power minus 2 and T power minus 2. So this is the formula for that characteristic dimension formula. So for each and everything in our fluid mechanics, mostly specific weight will be given, and it should be multiplied with the density. So I think so you could have a basic overview of it. So next one is specific volume. Specific volume is inversal of density. So it means specific volume equal to inverse of density, 1 by of density. So specific volume is also one of the most important thing that we need to look upon. Suppose if any kind of swing, suppose you just see guys, if the density is so much high, the specific volume will be so much lesser. If the specific volume is so much higher, the density will be so much lesser. For example, you take the density of the reference of the mercury. As mercury has so much density, the specific volume, it means the volume contained of the mercury will be so much lesser. But when you see upon the gases, you just take a oxygen. Thus, as the density is so much lesser, the specific volume will be so much higher. It just spreads around the entire container, entire area. So the next thing is specific gravity. Specific gravity is simple, guys. Density of a liquid. Wait, I'll just write. Specific gravity is equal to density of liquid divided by density of water. So density of water is a mostly of common thing. So in questions, most of the great questions, it means specific gravity will be given. For example, 0.8 specific gravity of oil. So 0.8 into 1000 equal to density of liquid. So like that we used to generally find out. So I think so you can have understand. And the next is specific gravity for gas being given, and density. So this is just common thing. And pressure means so much simple, guys. Pressure means this, you just consider this is a just surface. I am just applying pressure on it, means a force upon it. Pressure is defined as normal force exerted by the fluid upon per unit area. So pressure equal to force applied on a unit area. So that's a so simple formula, guys. So for force it's Newton, for area it's about meter square. So this is for, it means 1 Newton per meter square equal to Pascal. So I think so you can understand now. So next, the compressibility. So compressibility is also it means a simple thing. I think so you would have used a lot of syringe and like the injection thing. So whenever, so like this it will be. So we used to, what mostly we used to do, we used to place a finger here and we used to compress it. So this is a general representation of compressibility. So So it is common observation the fluid contracts more. It means whenever you apply pressure on a fluid, generally it should compress. But in our case scenario, the compressibility should be 0 because for incompressible fluid, it's given fluid, not liquid. Okay. If liquid means definitely it's incompressible, but fluid comes under the category of both liquid and gas. So gases are also being considered as a what? Compressible. So that's why we need to see for incompressible fluid the compressibility factor should be entirely 0. So I think so you can understand. And coming back to the bulk modulus is a little bit opposite to the compressibility. So fluid acts like elastic solid with respect. This is just a normal thing, but you just note this formula. So bulk modulus equal to change of pressure divided by change of volume of total volume. So this is a formula of bulk modulus. So bulk modulus equal to, it means how much we are changing the volume, that much the pressure will be changed. Mostly guys, in the formula the down sector we need to see while changing the down sector how much the above sector, it means the top one is changing. Suppose for example, how to say, I just couldn't find anything, but okay, let us consider this my hand. Like this, my hand is in a round shape, level round shape. So what I am doing is I am just changing the volume. So I am blowing the air inside or I am sucking the air outside. So while blowing and sucking, while blowing means my hand will expand. So the pressure also will tend to change. While I am just sucking the air, while just pulling the air from this area, the continuously the ball will shrink. So based upon this change of volume, how much the change is pressure. That's the thing that we need to look upon the bulk modulus. So when we come to the compressibility, it's compressibility equal to 1 by of bulk modulus. So you can see it means compressibility equal to minus dV by V divided by dP. So this is the compressibility. So here what we will do is, this is my hand. So I will just apply the pressure. It means I will just apply the pressure on it. So now the volume is changing. So while applying the pressure, how much the volume is changing. So that's one is called as compressibility factor. I think so you can understand now. Both are the just two things that are opposite to each other. That's it. See, and next thing you can see here, for isothermal means the temperature is a constant. So it means the temperature doesn't change. 10 degrees Celsius means only 10 degrees Celsius. No 11.7 degrees Celsius, no 12 degrees Celsius. I don't change. Only 10 degrees Celsius. So for that isothermal bulk modulus, KT equal to pressure. It means for bulk modulus saying, and for adiabatic bulk modulus equal to lambda of P. So this lambda I will just explain. It's adiabatic index. Later on I will just explain. So for this guy you can just give a explanation. You can see it's given bulk modulus. Bulk modulus means at the top sector what should be dP by dV by V. So but see guys, here thus they have given here, boom, they have just given here what density. You can see here there is a rho here. So we need to have a relationship with the density and the volume. So how we can just relate? You just think upon it. Just think. So there is a simple formula guys. It's like minus dV by V equal to d rho by rho. So for this there's a lot of explanation, but as the video proceeds I'll just, so you just memorize this formula. Minus dV by V, it's so simple. It's like a, it means specific volume with, you know, our specific volume equal to 1 by d of density. So we do have relationship between two each other, and other formula is also been added in this. So minus dV by V equal to d rho by rho. So while just putting dP by d rho by rho, so this rho will come automatically. So first option is the correct one. So I think so you can understand. And the next one is, you can see here, with increase in pressure, the bulk modulus of the elasticity, what it will happen? It will also increase. So you can see here guys, here as the pressure is increased, as the bulk modulus equal to dP by minus dV of V. So as the pressure is increasing, the bulk modulus also tend to increase. But when we see about compressibility, minus dV by V dP. So here while the pressure is increasing, what will do? The compressibility factor will decrease. So that is the indirect relationship between both of these. So next thing what's been given here, you can see the question number 2. So in here it's been given in a Quascan sea, and the density of water, the free surface is at the topmost point. It means there are two surfaces. Here at the top surface is the density rho, and as we proceed down, here it's the density, it means rho. So here neglecting variation in the gravitational acceleration, so G is normal and the bulk modulus K is normal, and the depth, it means here the depth h of a point from the free surface. It means they are asking h. So what is the value of h? They are just asking. So how we can just find it out? You just think it guys. Suppose, see, as they have been given here bulk modulus and change of density, you just make a relationship. Bulk modulus equal to what? bulk modulus is k equal to, see here question is, and question itself there has been a k is given, so k equal to, it means dp by dh by h, sorry, d volume of volume, so you just change it. So how to say, j equal to dp by d, it means d rho of density, because here density is given, so here the density difference equal to, down density will be so much higher, so density minus of what it will come equal to rho naught. So this is a just case scenario, so we'll just put it. So the other kind of thing, dp means change of pressure, so as we go downwards, the depth, as the depth is increasing, the pressure also will increase, so pressure equal to what, rho g h. So for dp we are putting rho g dh. So in this, for this formula, the third chapter will come, in that I will just explain. So you just substitute here, k equal to what, rho g dh divided by dp equal to d rho divided by rho. You just I think so you can have an understanding. So you just have to substitute now, make this downwards, and k equal to g dh divided by d rho of rho square. So you just make this in opposite way, and here g dh divided by rho square, k d rho divided by rho square equal to g of dh. So for h you will put 0 to h, and for d rho of rho naught. I think so you can have a understanding over it, and see, oh sorry, here it's about rho naught of rho. So next what will the formula will come, so k, I'll just put the line over here. So guys, something, it's about basic mathematical equation, that's it. So minus 1 by rho, it means here what will come, rho naught, and here rho equal to, next here as the dh is present, equal to g into h. I think so you can understand, and you can look over and just write in the pen, so you can get a clarity. So here you just put k minus 1 by rho minus 1 by rho naught, it means plus will come equal to gh. So h, they just ask h equal to, we just put k by g 1 by rho naught minus 1 by rho. I think so you can understand. So what is the answer? I see the C is answer. I think so you got my point, because here the calculation is only just mathematics. So that's it. So next question we can just see, when the pressure on a given mass of a liquid is increased from 3 megapascal, it means P1 equal to 3 to 3.5 megapascal. The density means density also changes. Density equal to 500 to 501. So as the density changes, what is the average bulk modulus? They are asking K. So K equal to what? Minus dP by minus dV by V. So sorry, plus. So minus dV by V equal to d rho divided by rho. So K equal to, what is the answer? Change of pressure. So 3.5 megapascal, it means you just put in the kilopascal, or megapascal 10 power 6 minus 0.0 into 10 power 6 pascal divided by minus dV by V. What will come? It's so simple, guys. We just put the density difference, minus d rho by rho. So what will come? 501 minus 500 divided by what will come? You just think it. So it's so simple. It's a original difference. It's 500. It's kg per meter cube. Kg per meter cube will come. So it's cancel. So in the upper point of view, what will come? It's about 1.5 into 10 power 6 into 500 divided by 1. So that's it. So you just make a multiply over it, and what will the answer become? So 0.5 into 500, it comes around 2005 into 10 power 6 equal to 250 megapascal. I think so you got my point. So next thing you can see, and see guys, here it's given in the IES 2020, and when the pressure of a liquid increased from 3 meganewton per meter square to 6 meganewton meter square, the volume is decreased. You can see the volume is even decreased. So the bulk modulus of the elasticity will be, so the pressure is P1 equal to 3 meganewton per meter square. So it's megapascal to 6 meganewton per meter square. So volume decreased equal to 0.1. So if volume is it's been not given 0.1, it's been given in percentage. So we need to consider the percentage. So into 100. So how much it will be? Minus 0.001. So I think so you can understand, because this thing is a procedure. It means not 100, but not 100. It's divided by 100. As a percentage is that, divided by 100 should be. So K equal to dV divided by minus dV by V, or dP divided by d rho by rho. So dP is how much? It's about 6 minus 3, and divided by 0. Total volume they are just totally given. So you can just put here what? 0.001. minus. So you just now do the calculation, and what the answer will come, you just tell me. So here 3 divided by 1 into 10 power minus 3 into 10 power 3 into, has the mega is given 10 power 6, so 3 into 10 power 9. So what is the answer? So B is the answer. Okay, I think you got my point. So okay, this was the next thing. So here the next Mach number is given. Mach number is one of the important thing that we need to look upon the entire jet point of view. So its Mach number is so simple, guys. It's the actual speed of fluid to the speed of sound. It means, as for suppose, if I'm just blowing the air, as I'm speaking, the air is coming outside of my mouth. So for Mach number equal to the air, what is traveling velocity of the air or velocity of the fluid divided by the Mach number. It means the speed of sound. Speed of sound. So mostly the speed of sound will be 330 meter per second, I think so. I'm not sure in it. So if Mach number is equal to 1, it's called as sonic flow. And if Mach number is less than 1, it's called as subsonic flow. If Mach number is greater than 1, it's supersonic flow. If Mach number is more than greater than 5 means it's called as hypersonic flow. So for most of the fluids we consider, as we see, is generally is less than 0.32. It's considered under the category of subsonic flow. Okay, I think so you can have an understanding. So next thing is vapor pressure. One of the most important thing that we need to look upon. This vapor pressure is a most effective and important thing, guys. See, in cavitation, first I'll just explain. See, for as the temperature around us is about 40 degrees Celsius to 1 atmospheric pressure. For example, how much the water boils? Water at 100 degrees Celsius with 1 atmospheric pressure, the water boils so much easily. Suppose if I just reduce the pressure, if I reduce the pressure to 0.5 atmospheric pressure, means the water will boil at 80 degrees Celsius. Wow, this is really amazing, guys. So as you see about when we go upon the mountain areas, hilly areas, as the pressure is so much lesser, so there water gets easily boiled upon. So suppose if I have a 2 atmospheric pressure, means I need to supply more amount of heat to the water. For example, 120 at 20 degrees Celsius only the water will especially boil. So the temperature is mostly depend on the vapor pressure. So you can see the vapor pressure of a liquid is defined as pressure exerted by the vapor in a equilibrium phase. You just don't consider this again. So it's so simple. If at a certain point of time, whenever the pressure drops, whenever it comes to low pressure, the liquid around us boils so much easily. For example, I'll just show here, and this is the submarine thing. I'll just increase. So you can see. So this is the submarine part. While it's been rotating here, there is so much splashes of water around it. So here the water gets easily boiled, because here the water, it means here the pressure will be so much low. So at a certain point of time, as the pressure is so much low, the water gets easily boiled upon. So if this water boiled upon, means what it will do? It will easily damage the entire the structure of the blade. You can see here little bit of components has been damaged. See, mostly it's not been shown here. Wait, just one sec. So this is a wow. What a beautiful. So you can see here. So entire is been damaged here. This is because of this kind of vapor pressure. So as this means as the water is rotating, here the low pressure is greater and the water boils so much easily, and this leads to damage. It means here the blade is there, and here the low pressure is being created, and especially the water gets boiled. So as the water gets boiled, means it will be full of bubbles. So the surrounding water will be so much. It means here the surrounding, it means at the end, it means, guys, let me just give you. See, here the submarine is there, and here the blade, and here the low pressure area. As the low pressure has been occurring, the water gets boiled easily. So as the water gets boiled easily, the water will come. It will be as a bubble, and it will come outside. So here the blade is there. As it goes into top reach area, here mostly water will be. So water will compress this small bubble. So tap, like that the bursting sound will come. So due to that, this kind of erosion of the blade will occur. I think so you can get me over basic point of view, and see, you can see here how much damage has been occurring in the blade point of view. See, this is the most complicated thing that's been in the submarine point of view. So not only in submarine, a lot of other aircraft and a lot of other sectors also, this kind of cavitation will occur. So what is the cavitation? So cavitation mostly depends on the phase equilibrium, because the phase equilibrium should be so much similar. And the other thing is cavitation number equal to PA minus PV divided by 1 by 2 rho V square. So P is ambient pressure, it means surrounding pressure, ambient pressure, and PV is vapor pressure. At which pressure? Vapor pressure. At the pressure, the automatically what will happen? The entire thing will just get evaporate. It means evaporized. And the rho is the density of liquid, and V is the fluid velocity, flow velocity. So you can see as submarine rotating here, the pressure is less. It means 2.34. It's so much lesser. So at the time you can see, guys, 1 centimeter of it means 1 centimeter of water, it just expands to 1605 centimeter cube. It's so much expanding. As it forms in the bubble, it expands so much. So as the bubbles is expanding, suddenly the water will force the vapor to collapse. So due to that, the bursting thing will happen, and the blood gets eroded so much easily. I think so. You can have a basic overview. And the next thing is, okay, let us see yes problem. And see here, guys, my handwriting is so much short, so don't just concern. For a certain torpedo which is moving at fresh water at 10 degrees Celsius with a minimum pressure given, it means this is the minimum pressure, and P naught is given 115 kilopascal, and density is given. So 10 degrees Celsius, it means at 10 degrees Celsius the minimum pressure is, it means the vapor pressure, it means what is given, the minimum pressure is 1240 pascal. So they are asking velocity. It means for cavitation number equal to PA minus PV divided by 1 by 2 rho V square. So as the question is given, so P minimum equal to P naught minus 0.4 rho V square. So what is the P minimum value? It's been given 1240 pascal equal to P naught value 115 kilopascal. See, there is a difference between pascal and kilopascal. Pascal is there, kilo, so into multiply 10 power 3 minus 0.4, density is 1000, and V square is the velocity. So you just make a calculation, 1240 minus 115 into 10 power 3 equal to minus 0.4, yes, 0.4 into 1000 V square. So how much it will come? 1240 minus 115, you just put a 110 and into 10 power 3, 10 power 2, you just made 400 to V square. So after just multiplying and just summarizing, what the answer will come, you just decide upon. So here as 10 power 2 is given, okay, at the end 16.86 meter per second it will come. So if at 10 degrees Celsius, okay, you just see 10 degrees velocity. If at 10 degrees Celsius, if you travel at velocity of nearly 16.86 meter per second, means if you travel more than this, means definitely the cavitation might occur. So that's why this calculation is entirely representing to us. If the CA is 0, means the cavitation tends to occur. Cavitation occurs. I think so we can have a basic understanding. I'll just put the next line over here. Okay, the next thing is, so next thing is, you can see here in the phenomenon of cavitation, the characteristic fluid property is involved in which one? Vapor pressure. It's been directly given here. The vapor pressure of the fluid characteristic is generally depend on the cavitation. See, if the cavitation parameter has been given 0, the local pressure is reduced to vapor pressure. Cavitation starts, boiling of liquid starts, cavitation. See, cavitation doesn't stop, but cavitation starts will occur and boiling of liquid occurs. So what is the option? And the local pressure is reduced to vapor pressure. See, yes, definitely. As we travel in a certain pressure, after this kind of thing, the pressure will definitely reduce. So the local pressure is reduced to the vapor pressure. See, guys, it's been given in the 2015. So one of the most important and easy question. So the answer is D. I think so you can have a good understanding based upon it. If you have any doubt, you just put in the comment section. So guys, I think so now we can just stop the section, and later on I'll just continue in the next episode. In the next video I'll just continue the next sections. Guys, let me end up this video. I think so it helped you a lot, and if you helped, you just put a like and just comment it. Okay guys, let me see you in the next video, then tada, bye bye, have a good day.